Hi, Professor.
Yep.
Um, I'm the student that came in late to the class. I signed up late. Did you send the email with like the syllabus and the website that you were going to create
Right.
yet?
I actually was worried about that when I sent it last night because I think I sent it via Blackboard and you might not have had
I
Blackboard access
don't.
yet.
I don't have Blackboard access.
I can just forward that to you right now. Also, where are the other people? That is a good question.
I don't know.
I'll do it to your Gmail address.
Perfect. Thank you so much.
Cool. Let's see. Okay, we have one more person. I'm going to wait a few minutes. Hey, I am not 100% certain if I have 3 hours of material today. So I'm actually teaching another summer course. Well, I'm TAing for a summer school to be more accurate, and it's not affiliated with Stony Brook. And the summer school currently has 10 people shy of 1,900 people in it. So like these are some big numbers. And I forgot that I signed up to teach a tutorial today there. So I had to prepare for that. And then there were people asking me for help. And then I really shouldn't have listened to those requests, but I did. So anyway. Okay, well, I guess I'm going to get started. So to remind us where we were last time, we were talking about first order linear ODEs. And so in general, we have two problems. The first problem is what we call the general form of a first order ODE. And this is of the form y prime plus f, which is some function of x. So I'll just write the variable explicitly, y equals g of y. And sorry, g of x. And the reason that this is a linear differential equation is because we don't have things like y squared or y prime appearing inside of it. And so we saw that, for example, if we consider the homogeneous version of this differential equation, which is the case when g equals 0, that we could add solutions of that equation together or scale solutions and they would remain solutions. And similarly, we could add any solution of the homogeneous problem to a particular solution of the general problem and still get a solution. And what I did at the very end of last class was to solve problem 2. So solving the homogeneous problem. And I'm going to review this because this is going to be very relevant for what we do today. So how did we solve the, why is there a squared here? That should be a prime. How did we solve the homogeneous problem? Can someone remind me?
A separation of variables.
Exactly. So we have that dy dx is negative f of xy. which implies that dy over y is equal to negative f of x dx. And then when we integrate this, I think I have enough space to write it here, we get log y is equal to negative the integral of f of x dx plus, and then I'll write my constant as log of c. And then exponentiating this, that gives me that this should be log y. Maybe I just wrote my y poorly. Y is c e to the negative. Well, I can write the integral, or I can write capital F of x, where capital F of x is some antiderivative of little x. And does it matter what antiderivative we take? Well, they'll differ by an additive constant, and that'll just be a multiplicative constant out front in the logarithm. So no, it doesn't. Now, the question is, okay, so this is the general solution to the homogeneous problem. And by the way, let me just emphasize something very, very important. Please do not memorize these formulas. I would be very unhappy if you pulled out the formulas that I'm about to derive on an assignment. I want you to actually do the separation of variables and solve it. I'm about to get to some other big formulas, and you shouldn't use these formulas. I just want to show you what the general solution is. It's much better to do it yourself. And the solution is much more readable. Okay, so now solving the general problem, there are going to be two methods for doing this. By the way, are there any questions about the solutions to the homogeneous problem? Because this is very important in what's going to come next. Okay, so there are going to be two methods. Method one is called the method of integrating factors. And so this is going to be a trick. And with almost everything we do today, it would be very hard to come up with this yourself. So we will multiply the equation by some function of x called mu. So we're going to take 1, which is this general form of a first order linear ODE, and we are going to multiply it by mu of x. And this is just some function of x. And so what we get as a result is that mu of x y prime plus mu of x f of x y is equal to g of x mu of x. Now, let's imagine that we had something nice happen. Suppose that the left-hand side had the form. So let's look at this. There's a y prime here, and there's a y here. And then there's a mu here, and then there's some expression here, right? Now, what sort of single expression would give us both a y prime and a y? So the answer is, let's imagine that it came from chain rule. Let's imagine that we took the function mu of x, y, the product, and we differentiated that product. Then what we get is mu prime y plus mu of x, y prime. So that recovers this term. And then the other term may or may not be of this form. And so we're going to choose a suitable mu so it is of that form. So suppose the left-hand side can be factored in this chain rule form as a derivative of a single term. Then we would have that mu of x, y, the derivative of this expression, was equal to g of x mu of x. And integrating, well, we know how to integrate a derivative, and this is just an expression of x. We would get that mu of x, y equals to the integral of g of x mu of x dx. And I'll write a constant here. Technically, the integral has the constant included, but in this case, I'll actually want to factor in the constants. I'll say this is a specific antiderivative, and I'll keep the constant here for future reference. Now, we haven't solved the problem yet because we don't know what mu is. So the question is, what is mu? Well, to get this, we want this expression, mu of x, y prime, which is mu of x, let's say y prime, plus mu prime of x, y. We want that to equal mu of x, y prime plus mu of x, f of x, y. So in particular, what's the interesting equality that we get? What two things do we need to equal each other?
If we had the u prime equal to u of x times f of x.
Perfect. So it's not u, it's mu. It's spelt mu. It's a Greek letter. So for your information. But yeah, you're exactly right. It's we want mu prime to equal mu of x, f of x. Because everything else is the same here. The only difference is that here we have a mu prime, here we have a mu prime f, right? Well, if you look at this and you consider this as an equation on mu prime, then what kind of equation is it?
Oh, it's homogeneous.
Exactly. So it's a homogeneous first order linear differential equation, and we know how to solve those. So isn't that great? So that implies that, let's say mu as the unknown now, mu prime minus f of x mu equals 0. And this is a homogeneous equation. So this trick, you wouldn't come up with it yourself. But if you just remember the idea of multiplying by mu and getting a chain rule factorization, then this is what comes up naturally. But again, most of the tricks that we're going to see today are things that are very hard to come up with on your own. Well, the solution, the thing is that we want a particular equation mu. We want some integrating factor that works. So we don't need the general integrating factor. In other words, we're not going to worry about constants at this stage because the constant comes up here, right? Does that make sense? So then a particular solution is mu of x equal. And so here we have negative f of x. And the two negative signs basically cancel out. So the solution would be e to the capital F of x. Where f is the antiderivative of capital F is the antiderivative of lowercase f. So this is what we saw from before. There's a negative sign here. That's why there's this negative sign there. So going back to our previous equation, and I'll label this equation with a star. What we get is this. So first off, I'm going to bring, I'm going to bring mu over to the other side. So I'm going to get that y is equal to mu inverse of the integral of g of x, mu of x dx, plus c to the mu inverse, c times mu inverse. And as a consequence, we have a particular solution for mu. It's e to the f of x. So y is e to the negative fx times the integral of g of x times e to the fx dx plus c times e to the negative fx. Now, do not memorize this formula. Please, for the love of God, do not memorize this formula. You are not allowed to use this formula on assignments. I will show you how you are going to actually do problems using this technique of integrating factors. But the point is that we have been able to find a solution for the general first order linear equation. And that's cool. And if you actually look at it, remember what I said last time, that every single solution is going to be a solution to the homogeneous problem. So see, this is a multiple of the solution of the homogeneous problem, plus a particular solution of the general problem. And in particular, the particular solution of the general problem that we get is this first expression here, and then plus any multiple of the solution to the homogeneous problem. So it's an affine space as I described before. Okay, you're not memorizing this. I'm going to show you how you actually write examples. And this is pretty interesting because I've discovered that when teaching Calculus B, a lot of the solutions were just strings of reasoning with sometimes other calculations interspersed inside of them. But my experience from preparing for this lecture is that in differential equations, you actually have to write a lot of sentences to make your solutions presentable. So I'm going to show you how to write good solutions. And I want you to write solutions like this on the assignments. So let's consider this equation first. Y prime plus 3 times x to the negative first power times y is equal to 5x. And by the way, I do want to actually emphasize one thing. Notice that the integrating factor that we're getting here is it's solved from the equation mu prime of x is mu f of x, right? So the integrating factor doesn't actually depend on g. The integrating factor depends only on the data of the homogeneous problem, which is something that I find interesting, right? Okay, so this is how you'd solve this problem. You'd write, we will find an integrating factor. Let's say we will first find an integrating factor. So what we remember from the previous solution is what the formula for an integrating factor is. And that formula is that mu prime of x is equal to mu of x f of x. So what we want is mu prime equal to, now what is f in this case?
Free x to the minus.
Exactly. So this is the equation that we want to solve, and then we're going to solve it by separation. So this gives us that d mu over mu is equal to 3 dx over x, right? And so integrating, and remember that we want a particular integrating factor. So we're not going to add the constants because we just want some integrating factor to give us progress, right? So what happens when we integrate?
Log of u equals free log of x.
Yeah, exactly. And then when I exponentiate, what do I get?
U equals e to the free x. Oh, oh no, u equals x cubed.
Exactly. So basically, when you have e to the log 3x, the 3 can sort of go out on the outside. And then 3 to the log x is x. So it's log, x cubed. So then we found our integrating factor, right? So we multiply the equation by x cubed to obtain. And then I know that I'm going to get a factorization here. So the factorization in particular is going to be x cubed y prime. And I can just write out what that's going to be. That's going to be x cubed y prime plus 3. And then if I multiply this term by x cubed, it's going to give me x squared y, right? So that's just this side multiplied by x cubed. And then I have to multiply this side by x cubed to get 5x to the power of 4. Right. Now, what happens is that I have this derivative and then this. And so I integrate both sides. And so I get that x cubed y is equal to the integral of 5x to the power of 4 dx. And I am going to actually want the constant now. So first off, if I integrate this, what do I get?
X to the fifth.
Yeah, because if I take the derivative of x to the 5th, the 5 comes down, and then I get x to the 4th. So that's good. And then the constant, well, there isn't like any particular form that's suggested here, so let's just put c. So let's not like min-max this at the moment. And what happens then is that we get that y is equal to dividing by x cubed everywhere, x squared, that's the particular solution, plus c times x to the power of -3. And that's the solution to the homogeneous equation. So I can also label that. This is a particular solution. And this is a solution to the homogeneous equation. And that's the answer. So isn't that cool? So this is how you write your solution. I would like for you to include both of these sentences in it. You can just follow my format directly and use it in every single problem where you use this method. I think this is a very clear and presentable solution. And then, of course, to understand it, you need to know what the method, what an integrating factor is. But we're going to assume that the reader understands what an integrating factor is. So under that assumption, this is a clearly presented solution. Any questions? Okay, let's do another example. So now let's consider the example y prime plus tan xy is equal to cosine of x. Okay, so we are going to find an integrating factor again. So we write first, we find an integrating factor. And then we write what the equation for an integrating factor is. It's mu prime equals what?
UF of U10.
Yes. And now when we separate this, what we're going to get is that d mu over mu is equal to tan x dx. And so as a result, logarithm of mu is equal to the integral of tan of x. Now, how am I going to rewrite tan?
Sine over cosine.
Good. And remember that cosine of 0 is 1, and that's tan is defined at 0. So it has to be cos that's on the bottom, not zero, not the thing that's 0 at 0 at the bottom. And then what substitution are we going to make?
I guess it's you could have U equals. Oh, it doesn't really matter. Oh no, cosec's.
Yeah. Yeah, cos x is the right one. I'm pretty sure the other one doesn't go perfectly. And so du, do you remember the sign?
Minus sign.
Good, that's correct. And how do I rewrite this in terms of u?
It's the integral of 1 over u. Oh, well, minus 1 over u.
Yeah, I'm going to put the minus sign up front. And okay, this is we're happy with. And then we'll add the constant as log c. And so substituting back, we get log of cosine of x plus log c. And so as a consequence of this, mu is equal to c. And then we have -1 times log cos x. So e to the log cos x is cos x, but then we have this -1 out front. So that becomes c divided by cos x. Okay, so now we found our integrating factor, and we say multiply by 1 over, I forgot. When we're doing integrating factors, we don't care about constants, because we just want a particular integrating factor.
But maybe with the substitution, it's good because let's say there was like a constant we couldn't have. Oh, never mind.
Because we add the constants later on. Because we have a constant here, so we get two constants and they would combine at the end, is what would happen. So the integrating factor is just something that lets us do this, because once we do this, we are able to get the general solution and the constants comes out from the second integration. And so when we do that, I'm going to write, let's look at what the original equation was. It was this. I'm going to write tan sine over cos. So I get to get y prime over, so you know what? I actually know that it's going to factor as the integrating factor times y, taking the derivative of that. So to get y over cos x prime equals, and then I write this equation multiplied by 1 over cos x. So y prime over cos x plus, so let's say sine over cosine squared y. And that's this side multiplied by 1 over cos x. And so what that equals to is this side multiplied by 1 over cos x, and so we just get 1. And then we integrate this. And when we integrate this, we get that y over cos x equals to, well, the integral dx, which is just x. And then here we add our constants, which I'm going to just add as c. And so that tells me that in general, y is equal to x cos x. That's the particular solution, plus any multiple of the solution to the homogeneous equation. So c cos x. And so what we learned is actually genuinely something new. We now know how to solve any first order a linear ODE. But I'm actually not going to be satisfied with this method. I'm going to teach you a completely new methods to solve this. And the method is going to use something called an ansatz. And what an ansatz is that it's an assumption that your solution is of a certain form, where making this assumption simplifies the problem. So method 2 will be known as a variation of parameters. So first off, suppose that y sub 1 is a solution of the homogeneous equation. So that is, if we look at y1 prime plus f of x y1, that's equal to 0. So y1 is a solution of the homogeneous equation, right? Then the general solution to the homogeneous problem is y is equal to some constants times y1, right? So any multiple of a particular solution to a homogeneous equation is also a solution to the homogeneous problem. And we're going to assume that like y1 isn't 0. because 0 will always satisfy it. So it's some interesting solution. Now, here's the ansatz. So this is guess as to what the form of a solution will look like. What we're going to do is we're going to say, well, if some constant multiple of y1 solves the homogeneous equation, maybe if we replace the number with the constant, which is just a number, with a function, maybe that will solve the general equation. So is y equals u y1, where u is u of x, i.e. some function of x. So in practice, if we ignore dividing by 0, every single solution can be written as a multiple of y1. If y1 is never 0, then we can divide by it. And we don't care about division by 0 in the points in which y1 is 0. So this isn't like too strict of an assumption to impose. And so we're just going to assume that our solution is of this form and see what happens, right? Then if y is a solution to the general equation, in other words, with g, we have so we start off with y, which is u y1 prime, plus f of x. I'm not going to write the x, I'll just write f times u times y1 is equal to g, right? Omitting it, all of the arguments. And so what does that tell us? Well, we can expand this to get, by chain rule, to get u prime y1 plus u y1 prime plus f of u y1 equals g. And then what we're going to do is we're going to factor this u out. And does anyone see what happens now? So what did we suppose about y1? Sorry, this isn't a u, this is a y1.
Scroll back down.
Yep.
Scroll.
It's on the screen.
About y equals c y1.
Well, we suppose that y1 was a solution of the homogeneous equation, right? So that says that y1 prime plus fy1 is 0, right? But look at what we have in this expression. So in particular, here we have y1 prime plus f of y1. So that's 0. So our assumption that y is a solution of the homogeneous equation means that this is 0, right? So that's the key trick. And so what we get as a result is that u prime y1 is equal to g. And so as a result, u prime is equal to g y1 inverse to the power of -1. I shouldn't say inverse. And as a consequence, u of x is equal to the integral of g of x times y1 to the power of -1. So this isn't the inverse. This is just the reciprocal. I could write this as g divided by 1 dx. And at this point, I'm going to introduce a constant as before. So let's imagine that this is a particular antiderivative and that I have the constant. And we haven't solved for y yet, right? Because we were given u. So if we think about what u is, sorry, what y is, we suppose that y is equal to uy1, right? So in other words, what we want to do to get y is multiply u by y1. And sorry, y1. And so if you actually think about this, this is a solution to the this is a particular solution. And this is the solution to the homogeneous equation by definition.
Wait, how did you go from that second to last line to the last line?
Yeah, so remember what our definition of, we had an ansatz, and this is a word that you should remember. An ansatz was an assumption that our answer had a particular form. So we want to find an equation y that satisfies the differential equation, right? So what we're going to assume is that our solution is of the form a multiple of y1, a particular solution to the homogeneous equation, times some unknown function u.
Okay.
And then what we did is we solved for the unknown function u. And once we solve for the unknown function u, we know what y is. It's that unknown function times y1, right? So going between these lines, I know what u is, and therefore I know what y is. Y is just u multiplied by y1. So I'll write this as y is equal to uy1. And for this reason, y is y1 times this, which is what I have here.
Okay.
Now let's compare this answer to the answer that we had before. Remember that our particular answer is of the form e to the negative f, capital F of x. That's a example of a solution to the homogeneous equation. And then what we see basically is that's the difference between u and mu sorry, the difference between y1 and mu is that they're inverses of each other. Sorry, the reciprocals of each other. So here we had basically in this equation, if we had mu inverse times this c mu inverse. And in this equation, instead of having mu inverse, we have y1. So in fact, that tells us that the integrating factor is just the reciprocal of the solution of the homogeneous problem. But that's basically what you do, because that's essentially what you're doing here when you're solving for the integrating factor. And so this version of the problem, it gets the same general solution. So we verified that this method works because we've recovered the same general solution, right? And so I'm now going to show you how to do some examples using variation of parameters. Right. So as an example of this, and I'm going to ask you to do some homework problems in each of the methods. And now I'm going to show you how you write up a solution using this. So consider the equation y prime minus, and let's say it's a function of t instead of a function of x for diversity. Right? So we're going to use, first, I'll write using the method of variation. Okay, first we solve the homogeneous equation. And the homogeneous equation is y prime equals t over t squared plus 1 y. And okay, I think we remember what's the integral. So, well, I'll just write dy over y is equal to t over t squared plus 1. The variable is now t, so dt. And so that implies that the logarithm of y is equal to the integral of t over t squared plus 1 dt. And I mean, I think I'd prefer you to actually do this, but we did this integral yesterday. It was like the first integral that we did. What's the answer?
One half log t squared plus 1.
Yeah. So in particular, you make the substitution u is t squared plus 1, and then its derivative is 2t, and so that's why we get a half. Now remember that we just want a particular solution of the homogeneous equation. We don't care about constants because we're then going to use it as an ansatz. So we don't have to use constants at the moment because we just want some solution. And so when we exponentiate, we get that y is equal to what?
T squared plus 1 to the 1 half.
Yeah, in other words, we can also, it's the power of 1/2 is also known as?
Square root.
Good. Yeah, so that's a nice way to write it. And so what happens then is that, okay, so we found the general solution. We will use the ansatz. You know what? Let's call this y 1 everywhere. Y is equal to u y1, right? In other words, u square root t squared plus 1. Yeah, I actually didn't have to put the y1 here. You know what? Let me undo that. Okay, this is, I'll just erase the ones. It has been a long day. Okay, so we will use the ansatz that y is equal to u times the square root of t squared plus 1. So u is an unknown function, and we just assume that the solution to the general equation is this. And so as a consequence, what we get is that y prime, in other words, u square root t squared plus 1 prime plus f, f is t minus c over t squared plus 1. Times y is equal to what? T, right? And so as a consequence, let's just use product rule on this. So we get u prime. Now, okay, square root t squared plus 1 plus u, and what's the derivative of this?
Minus 2t over square root t squared plus 1.
So it's the power of 1/2. So we just get, it wouldn't be a minus because this is that. But you're right otherwise. So you said t over t squared plus 1. Square root, right, at the bottom. Is that what you said? Except for the sign? Yeah, so here's what happens. When you take the derivative, you get a factor of 1/2 coming from the square root when you bring the exponent down, right? And then when you do chain rule and take the derivative of t squared plus 1, you get a 2t. So the half cancels out with the 2. So we get this expression right here, and then we have this expression, but notice there's a square root t squared plus 1 here, and there's a t squared plus 1 here, right? So we might as well cancel it out, right? So we get minus t over square root t squared plus 1 times u equals t. And so what do we see about these adjacent terms?
U.
Well, I mean, they cancel out, right? They're the same term. So what do we get? We get as a consequence that u prime is equal to t over square root t squared plus 1. Okay, and now I'm sorry, but usually you'd have to integrate this, but we know what the integral of this is because we just differentiated something, right? So I think we remember what the integral of this expression is. What is it?
Is it just square root of t squared plus 1?
Yeah, because we just differentiated that to get this expression right here, right? So sort of the question already told us what this integral was. I think that if you were trying to integrate it naively, you'd involve a trig substitution. And then let's add in the constant here. And so as a result, y, which is equal to u times the square root of t squared plus 1, is equal to what? Well, we multiply this by u, we know what u is, so we get t squared plus 1 plus c times the square root of t squared plus 1. And so you could have solved this method using an integrating factor as well, but now we solved it using variation of parameters. And so this is the second method. So this is the particular solution. Whoops. And this is the homogeneous solution. OL solution to homogeneous. And so we always get this pattern when we have linear differential equations, even of higher order. Except for the fact that we have multiple constants and multiple different solutions. In general, the amount of constants that you have is the dimension, the number of constants is the degree of the equation. So in a degree n equation, there would be n linearly independent solutions to the homogeneous equation. If you know some linear algebra, we're going to explain what that means later. But we're not doing higher order linear equations, and we will do higher order linear equations soon. And there will be some fun things involved with that. But I think that now is a perfect time for a break. And I think that I'm going to make it be a 15-minute break. So let's resume at 7:10. And this is only because I'll need to prepare a tiny bit more material. I think I have enough for the next segment, but I'll need some for the last segment. Any questions before then?
Yeah, I just had a question on, is there like a preferred method between those two? Or like, is there a difference on when you use one method compared to the other?
So I don't have a preference, and I think that the methods are about the same in complexity. On the assignment, sometimes I'll ask you to use a specific method, but if I don't ask you to use a specific method, you can use either method and then that would be fine.
Okay, thank you.
But it's good to know. And I mean, both of these methods are very interesting. So I guess the first method had to go first because it wasn't clear that the assumption, by making that assumption, we weren't somehow losing generality, whereas it was sort of convincing that we weren't losing generality here. With this method, the idea was that this is something they haven't seen before, the idea of making an ansatz, the idea of making a hypothesis about the form of the solution. And this is going to be something that keeps coming up in this course. Okay, see you at 7:10. Okay. Right. So I think I have enough for this section, and then I'll take a break in which I'll prepare one more example, and then maybe we might finish early. Again, there were some special circumstances today with the 2,000-person summer school. But what we're going to cover now is just some classes of special cases. First order ODEs. So remember, first order ODE is something of the form y prime is equal to f of xy, right? And the general interpretation of a first order ODE is that we have some direction fields and we're trying to find integral curves to the direction field, right? Now, in general, one of the special cases is when we have a linear first order ODE. And that's certainly one of these of a very special form. It's of the form f of xy plus g of x. But now there are going to be a few more cases. So one of these cases is the Bernoulli equation or Bernoulli's equations. Let's see how I spell this. So Bernoulli's equations are equations of the form y prime plus f of x y is equal to g of x times y to the power of n for n is greater than or equal to 2. Why n is greater than or equal to 2? Because if n is 1, then this just groups with the y and it's a homogeneous first order linear equation. And if n is equal to 0, then this just becomes 1. And then this is just a in general first order linear equation. But if n is greater than or equal to, then this isn't linear because we have like y squared or y cubed, etc., right? So this is not a linear equation, but we can solve it in general by reducing it to a linear equation. But it can be reduced to 1. And so how do we do that? Well, what we're going to do is we're going to divide this equation by y to the n. So we get y to the negative n times y prime is plus f of x y to the power of 1 minus n is equal to g of x. Now, look at this expression here, y to the power of negative n times y prime. Is there some way that we can write this?
It's like, well, it's like sort of like implicit differentiation.
Not yeah, I guess. The thing is that let's say we take y and what I'm going to differentiate some power of y, right? So is it going to be 1 more or 1 less than negative n?
One more.
Yeah, so that's when I add 1 to negative n, I get 1 minus n. And so when I differentiate this, well, the exponent goes down, right? So I get 1 minus n. Then I get y to the power of, I subtract 1 from this, negative n. And then because it's sort of implicit differentiation, as you said, because y is a function of x, instead of saying implicit differentiation, I want to say it's a chain rule, right? Because it's a composite function. So by chain rule, you get a y prime here, right? So in other words, if you look at this expression, y to the power of negative n y prime, it's we bring the 1 over n over. And so we get 1 over 1 minus n, y to the power of 1 minus n, the derivative of this. And then we get plus f of x. And then we have the same function, y to the power of 1 minus n is equal to g of x. So what we're going to do is we're going to perform a substitution. I'm going to say, let's say, what did I use? I used z, and you can tell that I'm a Canadian because I say z instead of z. So let z equal to y to the power of 1 minus n, right? So basically, y is some function of x and z is also some function of x. And so we're just going to let z represent this quantity. Then the equation becomes um, 1 over 1 minus n z prime plus f of x z is equal to g of x. And so, of course, what kind of equation is this?
Linear.
Yeah, so it's a first order linear equation. And we know how to solve this, right? So I could go back and I could write what the solution is. But basically what you have to remember is that at the very end of the equation, you should remember this, right? But anyway, so we've accomplished the problem of reducing it to a known problem, right? So let's do some examples of how we'd actually solve things. So let's consider the equation y prime plus y equals y squared. So how I would solve this equation is this is a Bernoulli equation. How do I spell it again? It surely is an R. I surely missed an R. B-R-N. Equation with n equals 2. So the only thing that we memorize from this entire process is that we make the substitution z equals y to the 1 minus n. So let's z equal to y to the 1 minus 2, which is equal to y to the power of -1, right? And so then we're going to go back to our equation, and we have thus, well, what is y? Then y is 1 over z, right? And 1 over z, the derivative of that, plus 1 over z is equal to, is equal to z to the power of -2, right? And if we take the derivative of 1 over z, what do we get?
Minus z to the, minus z to minus 2.
Right, and remember that z is a function of x, so we do chain rule. So we get minus z prime divided by, sorry, you made me say the American thing. How dare you? Z divided by, I'm joking, of course, z squared. So this is by chain rule, because z is a function of x as well. And then we put, so 1 over z is equal to 1 over z squared. And then, of course, we multiply everything by z squared. So we get, and then you know what? I don't want the minus sign on my prime term. I want to write it in the form that it's usually a linear differential equation. And we know that it's going to reduce to a linear differential equation because we showed that when we made the substitution in general, it reduced to a linear differential equation. So like you're not allowed to pull out this formula and memorize it. Instead, you make the substitution and just see that it becomes linear, and then you solve the linear equation. So I'm going to rewrite this as z prime plus minus, rather, because I multiplied everything by -1, minus z is equal to 1, right? So this is a good old linear differential, first order differential equation, and we know how to solve this.
Would it be
and so,
minus?
thank you. Good. Yeah, I multiplied everything by -1, and I forgot about that. So which method do you want to do? Choose variation of parameters or integrating factor. I guess we only did one problem with variation of parameters, whereas we did 2 with integrating factors, right? So let's do another variation of parameters one. So now solving this linear equation, by variation, we first solve the homogeneous problem.
I just have one question
And
regarding
yeah.
regarding the equation. I'm confused on where you got the negative z from.
Right. So let's look at this. We had this equation right here, and we made the substitution. Z is equal to y inverse, right? So y is equal to z inverse. Now, when we replace y with z inverse, what we have is the derivative of z inverse. And when you're taking the derivative of this, it's power rule. So the -1 comes out front, that gives you a negative sign here. Then you decrease -1 by 1, and so you get -2. And then by chain rule, z is also a function of x, so you get a z prime, right? Does that make sense?
Okay, that makes, yeah.
Good. And then I wanted this to be in standard form, so I multiplied both sides by
Okay, yeah.
-1.
All right, yeah. Thank you.
Good. So we're solving the homogeneous problem. And so the homogeneous problem is z prime is equal to z. Okay, that's not bad. So dz over z is equal to dx. So log, and remember, we just want a particular solution to the homogeneous problem at the moment, so we're not going to worry about constants. So log z is equal to x. And so z is equal to e to the x. So that is a particular solution of the homogeneous problem. Now, the ansatz that y is equal to what?
U of x times y.
Exactly. Times what in particular? Yeah, so e to the x is the particular solution, right? Actually, I've made a huge mistake right here. What we are solving, in fact, is the equation with the substitution. So I made this mistake before. The equation that we're solving is this equation, right? So there's no y, it's actually z, right? So it's actually z is equal to u times e to the x. We're solving this equation. We're not solving the original equation, we're solving this equation. So it's z equals u times e to the x. And then what we're going to do is we're going to plug this ansatz, assuming that it's a solution to this equation, and then we're going to solve for u. So what we get is thus u e to the x prime minus u e to the x is equal to -1, right? And then I do my product rule expansion here. So I get u prime e to the x plus u e to the x minus u e to the x is equal to -1. And we can see that these adjacent terms cancel. And so what we get is that u prime is equal to negative e to the negative x. And so as a result, u is equal to what?
E to the negative x dx.
Yeah. Well, we no dx because we just integrated it. And you can see that that answer is right because chain rule, it's e to the negative x times the derivative of negative x, which is -1. So we get that. So we're good. And however, since we've integrated, you know what? Let me actually write the integral. Because I prefer that you wrote the integral in this case. Because then you write the constants, right? So at this point, we're actually solving for u generally, and so we want the constant there to get our general solutions, right? Okay, well, if that's what u is, then what is z? What do we do to u to get z?
Multiplied by e to that.
Right, so e to the x times e to the negative x is 1 plus c e to the x, right? And now we have this in terms of z. Well, we want it in terms of y, and y is z inverse. So that tells us that y is equal to 1 over 1 plus c e to the x. And in the process of making this substitution, look, the constant ended up in a pretty interesting place, right? And notice that, remember, this equation was not a linear equation because we had this y squared here. And so this solution does not look like the solution to a linear equation, which would be a particular solution plus a multiple of a constant solution. We got this pretty interesting pattern appearing here, right? Sort of this part looked like the solution to a linear equation, but then our substitution actually had the reciprocal. And this would never be the solution to a linear equation in its own right. So that's pretty interesting. But now what I want to say is that I'm going to give you a second method. And I'm not actually going to give any examples for the second method, or maybe because I'm running out of material, I'll redo this example using the second method. So the second method is actually really cool. It's going to use an ansatz. And the idea is just because you can reduce to a linear equation doesn't mean you want to. You should. So in particular, we're going to consider the problem as before. It's y prime plus f of x, y is equal to g of x, y to the power of n for n is greater than or equal to 2, right? Now, what we're going to do is first, we solve the homogeneous equation. Or rather, let's, as we did for the variation of parameters, let's y1 be a solution of y prime plus f of x y equals 0. Right? So this is y1 is a solution of the homogeneous equation. Now we are going to use the same ansatz that we used in the variation of parameters. That y is equal to uy1. And so let's see if this ansatz works. Because assuming that we can divide by y1 freely, this doesn't constrain us. And let's see if this simplifies the question. So when I plug this in, what happens is that I get uy1 prime plus f of x uy1. I guess u is also a function of x. So you know what? I'm not going to write the x's. I'll write f u y1 is equal to g y. Now u, it's u, y becomes u. And then this becomes y1 to the power u to the n, y1 to the power of n. Right. Now, what I'm going to do is I'm going to expand this. So I get u prime y1 using product rule plus u times y1 prime plus f u y1 aha, I see what's going to go. I see what we need. Okay, I thought I was going to be a bit clever, but actually I'm not going to be a bit clever. Okay, at this point, it's going to be a bit unfortunate because I didn't actually ever want to let y1 be an arbitrary solution of this. I actually want to use the standard solution. We have that y1 is equal to e to the negative f of x, where f of x is the antiderivative of f, little f of x. So I actually do want to use this form, and it's actually going to be interesting. So what I get as a result is that u prime, so now forgetting about y1 and actually keeping it in this form. Now here's the interesting question. What happens when I differentiate e to the negative capital F of x? So we are going to use fundamental theorem of calculus, what I call part 1, but what people usually call part 2. What is the derivative of capital F?
Just F.
Yeah, little f. So what happens is that we're going to get e to the negative capital F of x, and then we're going to multiply by the derivative of this. And so that's going to be negative lowercase f of x, e to the negative f of x, right? By FTC2. So what happens then is that this term right here becomes negative u times f of x e to the negative f of x. And look what we have. The next term is f of x. I guess I'm writing the x's. U times e to the negative f of x is equal to g u to the n e to the negative n times f of x. And as we see, these adjacent terms cancel. So what we get as a result is that u prime is equal to g of x, u to the power of n, times e to the power of negative n minus 1 f of x, when I divide through by e to the negative f of x. And so when I integrate, what I obtain is that u is equal to the integral of g of x. Sorry. There shouldn't be a u. Yeah, there should be a u here. Right. Sorry, I'm doing separation of variables. So what we get is that du divided by u to the power of n, u to the power of n is equal to g of x e to the negative n minus 1 f of x. By the way, you are 100%. It's completely illegal to memorize this formula. You are not allowed to memorize this formula. Please don't memorize this formula. What we're just doing is showing that this process works. And we're basically practicing our calculation skills in the course of doing this. In a particular problem, you use this ansatz and then you solve the problem directly, right? But it's good because we're getting some practice. So when we integrate u to the n, this is u to the power of negative n. It goes up by 1, so it becomes n minus 1. And then that factor appears. So it's n, well, it's going to be 1 minus n. Let's see. Yeah, n minus 1. U to the n minus 1. You can check that my sign is right there. And so what that is equal to is that's the integral of g of x times e to the negative n minus 1 f of x dx. And so what we're going to do is we're going to bring this here, we're going to bring that down, and we're going to take everything to the power of 1 over n minus 1. So as a result, we get that u is equal to and then this is going to be in the denominator, so we're basically going to flip it to get 1 minus n. So we're going to get n minus 1 times the integral of g of x e to the negative n minus 1 f of x dx to the power of 1 over, and then it's not n minus 1 because this is at the bottom, so it's negative that, 1 minus n. I could write it like that. And then if this is my version of u, then remember that what I had was that I had the ansatz, y is u times y1. And if we remember what y1 was, it's e to the negative f of x. So in fact, I will just spare myself writing a lot of this over and over again. So y is equal to e to the negative f of x times this. Okay, do not memorize this formula. So here is a general formula to the solution of the Bernoulli problem, but again, you would never actually memorize this. All that you'd remember is that you solved a homogeneous problem and then you use the same ansatz that you did for solving linear equations. Now, for the sake of padding things, I will solve the problem that we had before using this. It would be nice if we solved a different problem, but okay. So the equation is y prime plus y equals y squared.
I just have a question.
Yeah.
If you scroll up a bit, I just have a question on why y1 equals e to the negative f of x, like that one. I'm just
Yeah,
still a bit
so-
confused on that.
The reason is that we're trying to solve the general homogeneous linear first order equation, y prime plus f of x y equals 0, right?
Yeah.
So remember at the very start of the lecture, we reviewed what the solution to linear, the homogeneous case, and it's just a direct separation of variables. So you start off with this equation, you bring the f over to the other side, so it's negative. You divide by y, you get this, then you get log y, then you integrate this,
Okay.
and then you get c, and then you exponentiate. So it's this.
So we just use the general difference here.
So in general, you should actually, when you're writing homework, solve this by separating variables directly.
Okay.
You don't
Okay.
remember this formula, don't memorize this formula.
Okay. That makes sense. Thank you.
So again, the only thing that you're memorizing is the ansatz and the substitutions that are made to solve this problem and the techniques. But in practice, you're solving everything by separating or solving first order differential equations using one of the two methods, linear integrating factors or variation.
Okay.
Okay, so let's go back to this problem and let's solve it. So the problem was y prime plus y equals y squared. So, okay, someone tell me, what is the process for solving this problem? What's the first thing that we do?
You solve the whatchamacallit, the homogeneous.
Homogeneous problem. Good, exactly. First and notice, by the way, that I'm saying what I'm doing. So when you're writing solutions, you should actually write English sentences that describe what you're doing, because that makes your solution more readable. And I want your solutions to be very readable. So you say, first we solve, you actually write that on your assignments. And so what we get is that dy over negative y, or rather, let's just make it simple, is equal to negative dx. So after integrating, we get that log. And since we're just going to use this for an ansatz, we don't need to keep the constants around in this case. So we get log y is equal to negative x. And so that tells us that y is equal to e to the negative x. Okay, now we use the ansatz. Y equals what?
E to the minus e to the minus x times some function.
Yeah, and we're going to call that function u. Good. Right, so when we have this ansatz, what we get is we plug that into this equation.
With homework, do we have to specify what mu is in this case, or is it just
So
like
what's happening is that we're going to assume that the solution is of this form, and then we're going to solve an equation that gives us what u is.
Okay. I was just talking saying that mu is a function, like we don't have to say anything regarding that before, like when we were saying ansatz.
Oh, there is a convention here being used here that's used just a function of x. It doesn't involve y, so I could write u of x. It's an unknown function of x.
All right, thank you.
So then we get y squared. So that's u squared e to the negative 2x. Because remember how sort of exponent laws work is that e to the x squared is by definition e to the x squared, right? But if you have something like e to the x and then you square it, that's different. That's the same as e to the 2x, right? So these two are very different expressions, right? Depending on how it's associated. Yeah, so that's that. And so what we do is we use product rule. So we get u prime e to the negative x. And then as you expect, we're going to get some cancellation. It always cancels, basically. So chain rule gives us a minus sign. And by the way, so you're about to notice that this method using the onsets is much quicker than the method that we had before. This is going to be a much shorter solution. So for Bernoulli problems, you don't actually want to reduce it to a linear equation. So what happens next is that we get that u prime is equal to, now we multiply everything by e to the x. So we get u squared times e to the negative x, right? And what do we do now with this equation?
Integrate.
What kind of equation? So, go ahead.
Do we integrate?
So the problem is that we have u on this side, right?
Separation of variable.
Exactly. This is a separable differential equation where u is a function of x. So what we get is that's du over u squared is equal to e to the negative x dx, right? So this is a separable equation now. So we don't have to go through the entire process of solving first order linear differential equations, which essentially involved making the onsets that we were going to make all along, didn't it? Because fundamentally what happens is that in the first method, we were going to make this onsets, but then sort of if you imagine what the substitution was, we essentially made the same onsets, except we had negative x this time because of that substitution. So this basically saves you a bunch of space. Anyway, so as a result, when we integrate u to the power of -2, so first off, it's -2, we increase that by 1, we get -1, right? And then what's the constant multiple?
-1.
So for example, this is u to the power of -1. So if we were going to differentiate this, we'd get the -1 out front, that would cancel, and then we decrease the power by 1. So we get 1 over u squared. So that's good. And that's equal to, let's actually write, okay, this is the easier integral. But I like to show where the constant comes from. So this is, of course, going to be e to the negative e to the negative x plus c, right? So that's 1 over u. And so what happens is then that u is equal to, so there's a negative sign here, there's a negative sign here, and it's 1 over u. So I'm going to multiply both sides by -1 and then take the reciprocal. So we get u to the 1 over e to the negative x minus c. And if you compare this to our previous answer, the only difference is that we had a plus c there, but replacing c with minus c gives us the same thing, right? So let's just sanity check that we got the same answer as before. Here we had c to the power of e to the x. Why did we have
Can I ask a question about the previous solution? I think it was at the bottom third row. We had something like du over u to the n.
Sorry, the general solution that we did here? Yeah.
The Bernoulli, yeah, here. Here, shouldn't it be 1 over 1 minus n times u to the 1 minus? We did
So
n
let's
minus
take the,
1.
the derivative of this. This is going to be u to the power of 1 minus n, right?
Yes.
And then let's divide this by n minus 1. And let's take the derivative of this. So what we get out front is, okay, yeah, so if we have 1 minus n, and we take the derivative of this, then we get the 1 minus n canceling out, and that's u to the power of negative n. So you're right.
And I think the same for the power of u.
The power of u is to the power of 1 minus n, but this is at the bottom, so it's n minus 1.
Okay, I see.
Okay, thanks. So, okay, somewhere we made a sign error, because these two answers do not. Oh, they do agree. They do agree. This is u, right? But what is y? Y is equal to u times e to the negative x. So what we do is we multiply the bottom by e to the x. Sorry, when we multiply it by the bottom by e to the x, we get 1 minus c e to the x, right? No sign error anywhere. And this agrees with our previous answer. There we had plus c, but the constant is any number. So this gives us exactly the same solutions, right? So remember, when you make an ansatz in the end, you have to return and actually solve for what the solution is. Because we were solving for u, but we actually want to know what y is. Does that make sense? Okay. I am now going to prepare one example, and I'm going to finish the class off with that example. But I actually need to copy this example from another sheet of paper. And so now would be a good time for a 10-minute break. So we're going to resume at 8:53, and then I'm just going to do one example. Well, one general method and then one example of that general method. Okay, see you in 2 minutes.
8:53?
That's an hour.
Sorry, 8:03. Sorry. Good, thank you. Okay, here we go. Good, I have the example. So now we're going to talk about one last class of special first order differential equations. And the name of this class is going to be super confusing. It's called a homogeneous equation. And this, of course, is distinct from a homogeneous linear differential equation. So yeah, the name is actually suitable, and this is the standard name for both of the concepts. And so the terminology has this. So if I just say a homogeneous equation, well, in this case, I mean something different from a homogeneous linear equation. So first off, we're talking about special first order differential equations. So what does a general first order differential equation look like? It looks like dy dx is equal to f of xy, right? Now, I'm going to suppose that the function is of a very special form. I'm going to suppose that it's some function that depends only on the ratio between x and y. So not every single function of x and y only depends on the ratio, because x and y are two different numbers, whereas the ratio is only one number, right? Now, so what happens is that suppose that we have an equation of this form. Then we're going to do an ansatz. And that's that y is equal to ux, where u is some unknown function. Now, what this implies, by the way, is that u is equal to y over x. So we're basically substituting in u for y over x. And that's why this is a very reasonable ansatz. So what happens when we do this is we get y prime. So ux prime is equal to phi of, now what is y over x? Yeah. So we get this equation. And so what's the results? We get that u prime x plus u is equal to phi of u. And I really like using Greek letters. So I've now used mu, I've used alpha, I've used gamma, and I've used phi. So you're going to learn a bunch of Greek letters this course. That's how it works. And so what type of equation is this?
Linear.
Let's see. No, because this is a function of u. It could be like u squared.
So then it's linear homogeneous.
No. It's not linear because this could be u squared. So in general, it would not be linear, but it is separable. If you want to see why it's separable, then what we have is that, well, I could write it as u prime is equal to phi of u minus u over x, right? And when I write it like this, it's clear that it's a product of a function of x with a product with a function of u, right? So it's separable. And so separable equations are good. We know how to solve them. So we get that's du over phi of u minus u is equal to dx over x. And so what we get from that is that the logarithm of x is equal to the integral of du over phi of u minus u. And then I'm going to add in the constant, and I'm going to call this log c. And so as a result, x is equal to c times the e to the integral of du u phi of u minus u. And now the answer is actually going to be of an interesting form. We have x is this, and we have that u is y is equal to ux. Now, what we could do is we could substitute, but what we're going to say is that this is a parametric form of the solution. So there's some other parameter, and if you know what u is, then you know what x is, and you also know what y is because you also know what x is, right? In this case, I'm going to allow you to not substitute back and just say that it's a parametric solution in terms of u, because it becomes a bit annoying when you do the other thing. So we basically parameterize the solution in terms of u, and that's a valid way of giving it. Now, okay, so that's the general solution. But once again, what have I been saying like a million times in this class? Please do not memorize this formula. You are not allowed to pull out this formula on an assignment. What you remember is the ansatz of substituting u equals y over x, right? That's what you remember. So let's do an example. And the example that we're going to do, and this is going to be my last example for today, is the equation y prime is equal to x squared plus y squared divided by x squared plus xy. Right? So first off, I want to see that this is a homogeneous equation. So, in order to do that, I divide the top and bottom of this fraction by what?
Let's say x squared.
Yeah, because I'd like to have the ratio y over x. And so I get y over x squared divided by 1 plus, and then I divide this by x squared, so y over x. So this is a function of this quantity depends on the ratio y over x alone, right? And so what happens then is that I'm going to make the ansatz. And the ansatz is u is equal to y over x. That is y equals ux. And so with this ansatz, I get ux prime is equal to what?
U prime x plus u.
Well, okay. I mean, I want to do this expression. What does this expression become in terms of u?
One plus u squared divided by 1 plus u.
Good. Now, what can you tell me? Actually, at this point, I'm going to do something. I'm going to then do this expression. So I'm going to do u prime x. And then when I take the derivative of x, I get u. And then what I'm going to do is I'm going to bring the u over to the side. And then I'm going to bring this to a common denominator. So I get 1 plus u squared minus u times what?
1 plus u.
Good. And what does that become?
One minus u over 1 plus.
Yeah. So the u squareds cancel out, and then we get a minus u here. Now, by the way, in general, you deal with something like this by doing polynomial long division. But if we did it here, it would be premature because we'd be subtracting the u over. Although actually it wouldn't matter because we'd take a u out front and then we'd subtract u, and then the subtraction would happen on the outside. So we could have also done polynomial long division here, but I first brought it over and then, okay. So at this point, this equation, I've already asked this question several times. Looking at this equation, what kind of equation is it?
Separate.
Yep. So it's separating variables. I get 1 plus u over 1 minus u du is equal to, and look, there was a u prime x here, so I bring the x over to the other side, and I get dx over x, right? And so what happens is then is that the logarithm of x, which is what I get by integrating, is equal to the integral of 1 plus u over 1 minus u du. And when I do this, what do I do now?
Oh, you could do well, I guess a v substitution.
Not necessarily. So this is a rational function, right? And there's a general procedure for integrating rational functions. And the first step of that procedure is to make the degree of the numerator less than or equal to the degree of the denominator. So we're going to do a polynomial long division, but we're going to do it manually. So we're going to write one negative. So there's a plus u here, and there's a minus u at the bottom. So let's consider the expression 1 minus u. How many of these are we going to have? What multiple should I put out front here? To cancel this. So there's a plus u here, and I want to cancel the u. So I'm going to write minus 1 minus u. So that's going to give me a plus u, right? Now, this is u plus 1, right? This is u minus 1. So in order to make this equation correct, what do I need to do?
Plus 2.
Plus 2. And so when I do that, these now cancel out. And so what I get is that this is minus 1 plus 2 over 1 minus u du. And I can integrate this. Well, actually, I'm going to clean up this expression a bit. This is a 1 minus u. I'm going to change this into a minus sign and a u minus 1. I guess it's a bit easier to integrate. Okay, so what do I get when I integrate this?
Is minus.
Would it be negative u minus 2 log of log absolute value of 1 minus?
Yeah. So because we're doing sort of this constant trick, we don't have to do absolute values when we integrate it,
Okay.
although that's more correct. And then we're going to add a constant. And what's the constant going to be?
Log of c?
Yeah, because we're about to exponentiate because we have log x here. So what we get as a result when we exponentiate is that x is equal to c times e to the negative, and then I guess there's okay, e negative u minus 2 log u minus 1. And I'm just going to split that. Right? And so when I split that up, it becomes a bit cleaner. So I get C. Now this is going to be -2, so we're just going to bring everything to the bottom. And then we get the expression u minus 1 squared, right? So that's the nicer way to write it. You should rewrite it like this. If you see log on top of an exponential, you should cancel them out, right? And then remember what our parametric equation is, and then we have y equals ux. And you know what? In this case, we can sort of, sure, make the system go away. So we get that, well, okay, we get x in terms of y, not y in terms of x. No, we don't get. So the problem is that we can't solve for one in terms of the other. This lets us parameterize it in terms of u. So this is sort of the best that we can get. Because if I substitute in, then it's not isolated for x because I have y over x here, right? And then how do I isolate with that? Well, that looks terrible. But here I parameterize both in terms of u. So if I give a specific value of u, then I calculate what x is. So I have that value of x, and then I multiply that x by u. And so that gives me a way to parameterize the curve. And that's why this solution is the better solution to use here. You can see in this example that it would sort of be, it would be really hard to isolate for one of the variables alone. And I guess that's the example that I'm 40 minutes early. Yeah, so this summer school that I'm running with 2,000 people, co-running with a bunch of people, it's a homotopy type theory summer school. And it's cool. But it took up most of my time today. So I am sorry about ending 40 minutes early, but I will take questions. So hopefully that will pad the time by 10 minutes.
I was thinking that for the homogeneous equations, it's sort of like to think of them, they're like about radial lines, they're all the same.
So if you actually think about it, y over x, yes, that's radial lines. I was actually thinking that before. So the ratio y over x, when is that constant? That's constant on a radial line, exactly. So in other words, the equation really only depends on the radial line. And so basically you're giving the function on a circle, essentially. If you give what the field is on a unit circle, then you get the field everywhere else. And then it's not defined here. But it is defined everywhere else. So you get a direction everywhere else that only depends on this circle. So that's a really good point. I was actually thinking about that before. Thanks. So remember, a general first order equation, it's a direction at every single point in the plane, right? Well, here what happens is that if you have a direction at some point, then it also has to be the same direction at every single other point on the radial line through the origin. So in other words, this is a direction field of a very special form where you only really have the direction fields given on the unit circle. That's the only information that you have. And from that, you extrapolate the direction fields everywhere else with it not being defined at the point 0, 0.
So you could make u in terms of like a theta and then do like, oh, you could make u tan theta and then it's like easier to graph.
Yeah. So in practicality, yes, I could try and do that substitution. In particular, having tans in the problem would not necessarily help, right? But yeah, you could do that. That's great. Good point. Okay, so I'm going to tell you what we're going to do next time. Next time, we are going to talk about exactness. And exactness is going to be a method that's going to solve. So every single first order differential equation presented like this can be solved by making it exact by multiplying it by an integrating factor, where integrating factor is used in a sense that's different from before. The problem is that that integrating factor isn't necessarily going to be a nice one. So you know what? I'm just going to impromptu this instead of ending 40 minutes early. I'm going to tell you, and then I'm going to do this again at the start of next lecture. I'm going to tell you about exact differential equations. So the thing is that imagine that we have that dy dx is instead of saying that it's f of xy, I'm going to say that it's f of x y over g of xy. It's just as general, right? Like you could make g of xy equal 1. Now, the thing is that I can rearrange this equation to read f of xy dx minus g of xy dy is equal to 0. Now, okay, the minus sign is silly. So consider instead f of xy dx plus g of xy dy. Now, this equation is actually going to be slightly more general than this equation. And the reason is that sometimes g is going to be 0. And when g is 0, you're going to be dividing by 0. And it's going to look like dy dx is undefined, right? But here, you're not dividing by 0. If f and g are defined everywhere, then this equation also lets you say when a slope is perfectly vertical, right? So if dy dx is 0, it's horizontal, but if it's infinite, it's vertical. But if I write an equation like this, then I can also account for the vertical cases. So in general, we're going to be working with first order differential equations of this form, where we just like push rigor to the side and split up the dy and the dx. Now, what happens is, suppose that's sort of something like k of x comma y is a function. Then there is something known as the total derivative. And if you've taken calculus 3, you will have encountered it. I'm not sure if calculus 3 is a prerequisite to this course, though, but it sort of doesn't matter because I'm going to tell you what this is. So dk I'm not going to write the thing, is known as the total derivative. And this is equal to the partial derivative of k with respect to x times dx plus the partial derivative of k with respect to y dy. Now I'm just going to tell you the punchline. Suppose and so what the partial derivative is that you differentiate it with respect to x, imagining that y is just a number. Or you differentiate it with respect to y, imagining that x is just a number. So instead of chain ruling, the derivative is actually 0. Now, suppose that our equation f of x comma y dx plus g of x comma y dy is actually something of the form dk. Then the result is that the solutions are k is equal to c. So how you think about this is that imagine that you have a function of a single variable. Well, the derivative, it's sort of a linear approximation to the function. Now imagine that you have a function of 2 variables. So how you think of a function of 2 variables is that you sort of have the x-axis and then you have the y-axis. And then you also have sort of the z-axis in 3 dimensions. And sort of the z-axis is going to represent the value of f of x. So imagine that we have some sort of surface in 3 dimensions. And sort of this is, I mean, it's interesting. So it's some sort of 2-dimensional function. And then suppose we have a point here. And what happens is that this surface has a tangent plane, right? So I'm going to cover this in a bit more detail next time. And so the point is, if you change x by a bit and you change y by a bit, then how does the value of k of xy change? And the answer is, well, if we just change it with respect to x, then y is just constant, right? So it's going to change. The local linear approximation is the partial derivative of k with respect to x. Now, what happens if we just change y without changing x? Well, then x is constant, and what we're going to get is the partial derivative of k with respect to y. That's going to be the slope of how the surface curves in that direction. Now, what happens if it goes in a direction that's not x and y? Well, the idea is that it's actually a plane that's approximating it. And so you can actually get that by getting a linear combination of the partial derivative of x with the partial derivative of y, depending on how far you move along the surface. So if, for example, if you move 1 unit in x and 1 unit in y, then it's going to be the sum of these 2 partial derivatives. That's going to represent the slope of the line there. So it turns out that because it's a surface that's approximating it, you only need to know the slope in one direction and the slope in the perpendicular direction. And from that, you can discover the slopes at every single other angle on the surface. And so what happens then is, suppose we're saying that basically dk is equal to this. Well, we want to solve for this equals to 0. So saying that sort of the local linear approximation to this is equal to 0 is the same thing as saying that k doesn't locally change, which is globally amounts to saying that k is constant. So what happens is k is going to be a function of x and y. And so then k, whoops, I want to change colors. The solutions to the equation are sort of going to be the subsets of x and y in which k is flat. So how you think about it is sort of imagine taking a plane that's perpendicular to the z-axis, right? And then imagine intersecting it with one of these. And so that's going to be a level surface. So for example, if you have a mountain, how do they draw mountains on maps? They give contour lines, right? So along this line, every single point has the same elevation. Right? So imagine how this would look like 3-dimensionally. There's like a circle here, then there's a circle here, and then there are 2 separate peaks, right? With the elevation increasing as you go to the more inner circles. And so what happens that is if you have this whole surface and you're actually trying to solve this equation, it would sort of be the contour lines of that surface with respect to heights. That's what the level curves would look like. And so these level curves as a subset of the XY plane are going to be the solutions to this first order differential equation. So that's a bunch of abstract stuff, but that's how you picture the solution to this equation. And so the question is basically, when is a differential equation exact? And I guess I'm going to cover that now. So the thing is that if okay, no, I'm not going to cover that now. I think I'm probably going to make a mistake. It's better if okay, it's good because I motivated the concept. So the idea is we're going to ask the question, when is something like this of the form dk? And then what's going to happen is that in general, this equation is equivalent to this equation if we multiply everything by some function, right? So if we multiply this by some other function, then we still have the same differential equation because we can divide by it. And so the thing is that we are going to multiply it by some equation so that it becomes exact. And the equation that we're going to multiply it by is going to be known as an integrating factor. And in general, every single differential equation of this form can be solved by multiplying it by a suitable integrating factor. But the problem is that that integrating factor might not have a nice formula. This is just an abstract result. But we're going to give criteria for when the integrating factor can be found in a nice form. In particular, it's going to depend on sort of the difference between partial derivatives of f and g divided by f. So it turns out that if that expression sort of has a nice form, then you get an integrating factor, and that's sort of random. But the point is that when that random thing occurs, you actually get integrating factors, and then you're able to solve the equation pretty directly by just doing this. And what we're going to see is that the question of whether this is exact or not actually reduces down to a differential equation. And then we can try and solve that differential equation. So that's what's going to happen next time. And I guess this is a good stopping point because what did we cover today? So last time we talked about separable equations. That took a while, and then we played around with Racket a lot, looking at what the separable equations look like. And then we started talking about linear differential equations and then linear first order differential equations. And we solved a homogeneous problem, but now I solved a general problem here, and we had two methods of doing. So we had the method of integrating factors in this sense, which is going to be different from the method of integrating factors next time. And then we had the method of variation of parameters. And then we saw that we could use either of those methods. And then we looked at some special classes of equations, which are not linear, but which can essentially be reduced to linear equations, or in the second case, we didn't even reduce it. We just directly solved it by separation after making a certain substitution. And sort of with the integrating factor method, this was like a pretty cool trick. But when we got to the method of variation of parameters, we introduced a new concept. And that new concept was the concept of an ansatz. It's assuming that the solution has a certain form. And then everything else that we did related to using ansatzes. And it's a German word. I should probably know what it actually means in German. But I mean, in English, it means a hypothesis made of a solution of a problem. And it comes from physics, from German physicists. Right. And so here, the ansatz was that, well, we were going to replace the constants in the homogeneous solution with a general function. And apparently that lets us solve it because I've shown here that that gives us a general solution. Then we talked about two types of equations, Bernoulli's equations, which for n is greater than or equals to 2 are not linear, but they can be reduced to a linear equation. But this method is actually too long. You shouldn't reduce it to a linear equation. What you should do instead is that you should use an ansatz. You should solve the homogeneous equation, and then you should use the same ansatz before of changing the constant to a u, and that solves the problem in general. And then I gave an example of solving what we had before using this. And then we saw that we got the same answer and that the solution was shorter. And then we also talked about homogeneous equations in a different sense. So not linear homogeneous equations, but homogeneous equations in this sense. And what's your name? How do I pronounce your name? Elisha?
Alicia.
Elisha. So what Elisha suggested very cleverly was that what's really homogeneous equations look like is that there are equations where the direction only depends on the radial line. And so in that case, which is a very special case of a direction field, what you do is you use the ansatz y equals ux, which represents substituting u equals y over x, and then rewriting the equation, and then we could just solve it by separation of variables, which is even easier than solving a first order linear equation in the general case. And so that's what we covered today. And then I hinted that next time we're going to look at equations of this form, which is essentially the same as considering an arbitrary first order ODE resolved with respect to y prime. And then I suggested that, well, if this expression is actually the total derivative, where the total derivative is just defined as this of something, then a math fact is that the solutions to the differential equation are exactly given by the level curves of this surface. And so the question is, when is that going to happen? We're going to reduce that to the problem of differential equations, and then we're going to give a bunch of cases in which those differential equations can be solved. So that's what you can look forward to next time. And okay, so that next time is on Monday, and then I should tell you procedural things. So tomorrow I actually have free time for once. Just before this course, I spent 2 weeks traveling at, there was a big conference that was very important. So I have not had free time just before this course, but tomorrow I have free time. So I'm going to write up the first assignments and I'm going to post that by midnight. And I'm also going to create a course website and I'm going to post a bunch of stuff on the course website. And then the first assignment will be due a week from then, right? So midnights on the Friday of the following week. And what is the assignment going to cover? Well, it's also probably going to cover the stuff that we cover on Monday. So exact first order equations. Sounds good? Okay, cool. Have a good night and see you on Monday, and expect an email from me with information by midnight tomorrow. Bye.